Good afternoon, everyone. Welcome to the new episode of the QuEra with friends, together with our colleagues and partners from Australia. My name is Tommaso McRee. I'm the Executive Account Manager at QuEra Computing, and I'm happy to introduce our guests for today's presentation. The first one is Ugo Varetto, the CTO and Interim Director of the Quantum Supercomputing Innovation Hub at the POSI Center. Then we have Pascal Elahi, who is the Quantum Supercomputing Research Lead at the POSI. And then Michael Biercuk, who is the CEO and founder of Q-CTRL. The agenda for today's presentation will start with a brief presentation from QuEra's side, telling a little bit about the technology that we've been developing at QuEra Computing, followed by some consideration regarding the latest development at the commercial level. Then I will pass the word to the POSI Center and Q-CTRL respectively, come back for some discussion about opportunities for collaboration and a brief conclusion. So why don't we start? Let me say that QuEra is a quantum computing company that is currently headquartered in Boston. We employ more than 50 between scientists and engineers. We are very close to the campus of Harvard and MIT. And by now we have offices also in the UK and Japan. The mission of the company is to build and commercialize the quantum computers based on neutral atoms that are sufficiently large scale and also resistant to noise. We also productize innovation as a core business of our enterprise from QuEra and our partners at MIT and Harvard at very high speed. Commercially speaking, we already collaborate with dozens of organizations that execute jobs on our quantum computer regularly. For those who are part of the young generation and are interested in opportunities at QuEra, also feel free to check our career webpage. We are constantly hiring and scaling up our business. Let me tell you a little bit about the technology that we've been developing. So first of all, why neutral atoms? We believe, and also the community believes, that neutral atoms are among the most promising approaches to perform quantum computing. First of all, one of the main reasons is that we employ neutral atoms, which are nature's perfect qubit, in the sense that differently from artificial qubits, neutral atoms respond to external fields all in the same way. So they don't necessarily need to be characterized individually. They are also relatively easy to scale. Right by now, we have machines with hundreds of qubits, and there are lab demonstrations with thousands of qubits. And we believe that within the current technology, we can scale these systems up to tens of thousands, if not hundreds of thousands, without requiring additional hardware development, namely interconnects. There are also techniques that make this technology particularly efficient. For example, a specific tool developed within the collaborator that we are interacting most frequently with, which is called qubit shuttling, that allows a very efficient problem encoding and also easier quantum error correction algorithms implementation. Last but not least, our systems as of today operate at room temperature, meaning that we don't need any additional cryogenic tools, so that we can reduce the footprint and the complexity of our systems. By now we have our first quantum computer, which is called Aquila, that completed 2 years on November 1st, 2024. As we speak, it is still the first and the world's only publicly accessible quantum computer based on neutral atoms. And over the past couple of years, we really did a great engineering effort to increase the availability window of this device from a few hours back in November 2022 to about 130 hours today. We explore a number of applications together with our customers and partners, and these applications span 3 different areas or classes of problems that belong to the machine learning realm or quantum machine learning or classification, regression, and prediction tasks. In particular, we developed an algorithm that we call quantum reservoir computing, which is particularly suited to the specific capabilities of our quantum computer. The second class of problems is called the quantum optimization or combinatorial optimization that builds on top of a specific problem that we can solve within our hardware, which is called the maximum independent set problem. But let me also mention that there are other problems that are not necessarily native, such as QuEra problems that are particularly relevant for commercial applications that can still be mapped with on our quantum analog quantum computer Aquila that can be solved with an additional overhead with respect to the number of variables that can be mapped into our qubit system. The third class is inspired mostly by academic application. It's called the quantum simulation. Initially, it was originated from an idea of Richard Feynman, Nobel Prize winning physicist more than 40 years ago, to essentially simulate quantum mechanical systems with other quantum mechanical systems that we can control and tune with very high precision. Within quantum simulation, the most sort of notable problems that can be addressed are, for example, equilibrium and non-equilibrium phases of matter, and also more fundamental problems in physics or chemistry, such as lattice gauge theories. More recently, over the past year and a half or two, we started to sort of focus our attention more and more towards the so-called digital or gate-based quantum computation. One of the reasons why we pretended to do so is the fact that typical error rates of physical qubits are too high for most practical applications. One way to sort of overcome this problem at the architectural level of basically building quantum computing is to essentially employ a technique that sits at the interface between physics and mathematics that is called the quantum error correction. At the core of the theory of quantum error correction is the so-called logical qubit, which is a set which corresponds to a set of physical qubits, such that when we do operations with the logical qubits, if the fidelities of the operations at the physical level are sufficiently high or above a certain threshold, we can expect that the operations at the logical level behave better or with better fidelities as we scale the size of the logical qubit with respect to the number of physical qubits. Now, this reduced error rate allows in principle for longer and more meaningful quantum algorithms. All these ideas sort of led to a number of breakthrough demonstrations that started back in December 2023 and were recently upgraded to a very recent demonstration back in December 2024 of magic state distillation at the logical level, thanks to the development of our second generation of quantum computer that is called Gemini. Gemini is a quantum computer built natively also for integration with HPC Center. Is a digital QPU with hundreds of qubits today that will scale to thousands of qubits very soon. It is easy to install, as you can see it has a relatively small footprint. It doesn't require any cryogenic cooling, and it consumes also very little, especially when you compare this power consumption with the standard classical HPC systems. At the practical level, we plan to employ our quantum computer to co-develop applications that also in the very short term will involve early demonstrations of quantum error correction. And we plan to do so together with our direct collaborators as well as with the users from different HPC centers. At the commercial level, QuEra has been happy to announce very recently also a strategic investment from Google that will essentially boost the technological development done over the past few years. And then more at the level of really selling quantum hardware, we recently signed 2 important contracts, one with the UKRI, which is a British research and innovation branch of the UK government, to install a tested machine in hardware at the site of the newly created National Quantum Computing Center, and also the possibility or the opportunity to install a fully functional quantum computer at IST, which is the equivalent of NIST in Tokyo, together with the strategic collaboration together with NVIDIA. So with this, I would like to stop here for a few minutes, pass the word to our collaborators at POSI. So please, Pascal and Ugo, feel free to start the presentation. First of all, you can also, I think, also briefly introduce yourselves.
Yes, thank you, Tommaso. Let's see.
Yes, yeah. I think we can see your presentation. Please.
You're the one.
Hold on, let me grab, I don't know why it's the older one. Yeah. Apologies. We can edit this out though if we need to.
It's good way of recording, can always. Yeah. Can always cut.
Just don't understand why it's the old one.
I mean, I can speak over anything, but if it was, yeah, this is the new one. Yeah, the new one. Yes.
Yes. There we are.
Ugo, why don't you introduce yourself?
Yes, so we can start doing that while we're. So, thank you, Tommaso. I am Ugo Varetto, Chief Technology Officer at the POSI Supercomputing Center. And since we started with the Quantum Supercomputing Innovation Hub 2 years ago, I'm now also interim director of the newly created center.
And I'm Pascal Elahi, so I'm the quantum supercomputing research lead here at Pawsey, leading a team exploring the intersection of HPC and quantum computing. And I will let Ugo start.
Okay, very good. So thank you. So in this presentation, I'm going to introduce the POSI Supercomputing Center. I'm going to explain how we got into quantum computing, also describing some of the activities we are carrying out at the moment. And then Pascal will cover collaborations, right? Specifically the collaboration with QuEra. So the POSI Supercomputing Center is a center similar to many other centers around the world. We support many users, many research projects, about 42 research institutions, and pretty much any scientific field you can think of, right? We also invest a significant amount of resources into education and training. Last year, and the year before as well, we contributed to about 200 training programs around the world, not just here. The one thing that makes us kind of unique is the fact that we also need to support the radio astronomy projects, which do require ingesting, processing, and storing data 24/7. This is data coming from radio telescopes in the desert up north. And so we constantly ingest and process data here at the center. One interesting fact about radio astronomy. So the radio astronomers started looking at quantum computing back in 2021. Specifically, they were looking at quantum machine learning applied to pulsar classification. There are a few papers published using Born machines to do that kind of perform that kind of task. And so in the future, it might also happen that we will be collaborating with them also in this specific field of quantum computing. POSI is a joint venture of 4 universities and the National Research Organization, CSRO, and we have been operating since 2013. Now about quantum computing. So we started looking at quantum computing in 2020. The reason for doing that at the time was because one of our mandates is to constantly look at new technology, right? Like we did in the past for GPUs, FPGAs, and other things, right? And so that's why we started looking at quantum. However, it was hard to get started. So what we did was to start a partnership with, at the time, the only quantum computing company in Australia who had a device that could be deployed here in the white space at our center. Room temperature without requiring cryogenic infrastructure. So that's why we started partnering with them at the time. But the issue is that as soon as we started looking into quantum, we immediately realized that it's not enough to just develop the hardware, but there are a lot of challenges that require addressing as soon as possible, right? Specifically, integrating quantum computers with classical supercomputers and enterprise type of infrastructure, community access, giving access to quantum computers that students and researchers can use to experiment with the technology, upskilling people both in academic and industrial environments, and of course, developing new algorithms, right? Because you cannot just go ahead and port the current classical algorithms to work on a quantum computer, right? As you know very well. So we also started dedicating some resources together with some university here to this specific challenge. So we then received money to start this Quantum Supercomputing Innovation Hub from the federal government. And the idea is to have this new center serve as a collaboration platform focusing specifically on integrating quantum and classical computing with the goal to accelerate scientific research in general, right? And what we did was to work on a strategy which is based on three main pillars, which are innovation, education, and inspiration. Yes, so about innovation. So as I said before, in 2022, we deployed the first ever room temperature quantum computer inside a data center alongside our main HPC system, together with Quantum Brilliance. We then started working on this portal to allow researchers to use a single access point into quantum computing resources on-prem and off-prem, also integrated with regular supercomputing infrastructure. So we are still working on that portal together with AWS mainly. And the other thing we did was to deploy the first Grasshopper cluster here in Australia, focusing mainly on simulation, but going forward also on using GPUs to address error correction challenges, right? So we'll see how it goes, but if we ever have to, or we're planning actually to deploy in the future a quantum computer here on site, and the plan is to use the GPUs there to help out in addressing error correction, right? That's what we're thinking of doing. About education and inspiration. So there are two pictures here. One is from the bootcamp we ran last year in February, March. It was a 2-week training program developed together with an external company and a couple of vendors, where we even used some real-world use cases that were addressed as part of the training program, right? And then on the right is an animation, actually, of the Quantum Girls event we ran at Pawsey. So in order to inspire people, right, we're now targeting young generations, right, of students, and we're involved in quite a few programs there together with universities. And one thing we are doing these days, for example, is to work with the University of Western Australia on games, like board games, right, or Dungeons and Dragons type of things, right, to make quantum computing accessible and fun. And this is the end of my part of the presentation. And I'm going to let Pascal continue the presentation. He's going to introduce the team and then talk about collaborations. Thank you.
Thanks, Ugo. So as we Go mention we have a team. It is a small team at Pawsey because of Pawsey is principally a supercomputing center, but we have this quantum innovation hub. The team consists of myself, Shusen Liu, who's based at Sydney, Edric Riev, who's based here at Pawsey, and Casey Myers, who's based at UWA and at Pawsey. And this small team has, we have a variety of skill sets, but basically we are looking at quantum computing and HPC. So we usually all have those sets of skill sets. The focus internal projects are on integration of quantum computing with HPC. As we mentioned, one of the challenges is that you really can't use quantum computers on their own, and that they solve portions of a problem. And that portion of the problem, it can be very intractable on a classical computer, but you might want to, and usually complement that with a real classical computer. So that integration is a key component of probably deploying hybrid workflows that then can solve real world problems. Part of that also is looking at hybrid quantum computing, looking at developing the infrastructure necessary to do this, looking at quantum simulation as well. So we have also a quantum computing simulation cluster that has the Grace Hopper nodes. But a lot of the simulation hardware that exists out there actually is quite bottlenecked by how big a simulation they can run. And of course, you'd like to run and test qubit scales of, tens to hundreds might be a challenge, but at least up to scales of tens easily. And that requires significant quantum computing resources if you want to do the actual quantum computing simulation. But if you also want to simulate it, that requires probably actually a couple of GPUs. So an actual cluster, but also our software development. So we are in that space of doing the software development, testing, and benchmarking to enable efficient quantum computing simulation. Part of that is also development of quantum computing algorithms and development. So, we have a few team members who are very focused on that aspect of the quantum computing research. And we're looking at both near and far terms. So noisy and then eventually logical. But, something that you can implement now and test now, and something that you could aim for and try to develop the error correction for. And so you can test later on when the devices become less noisy and there's more qubits to do the error correction. We're also looking at developing educational material. So that's part and parcel of almost all the quantum computing centers, right? They develop educational material to assist researchers who might be in a specific scientific domain and have that expertise and knowledge and might have some computing knowledge, but then are lacking the quantum computing expertise to translate the challenge that they're facing into a quantum computing algorithm and then solve that challenge. But we're also looking at high school. So not just researchers at university level, but also high school students, inspiring high school students to enter the quantum computing field. So a good idea to give the roadmap of the current recent sort of work that we're doing. So in September, right, we developed this quantum computing projects with QuEra, where we are looking at exploring a couple of different quantum computing algorithms. But we are also, as I said, complementing that real-world quantum computing access with also quantum computing simulation in partnership with NVIDIA, where we've opened up this specific dedicated cluster to quantum computing early adopters, as well as Pawsey interns and the team, so they can really start exploring and testing quantum computing algorithms up to 30 qubits, up to 40 qubits, right? Some really interesting scales where you might be challenged. Most quantum computing researchers have focused on something they can run on their laptop, and that limits what they can actually run and test. So now we're really opening up that pathway so they can explore and do much larger qubit counts. We're looking to democratize access to quantum computers by developing this portal. So one of the challenges I think a lot of quantum computing researchers face is they might be simulating on their laptop, and they might have limited access to a quantum computing device, maybe an IBM machine, and that's it. Just because they may not have the budget to necessarily pay for quantum computing access where the end goal is research, right? You're still trying to develop the algorithm and test it. By this way, we can, at Pawsey, provide a single access model where people can try a different variety of quantum computing hardwares in an exploratory fashion where they are not necessarily contributing thousands of dollars to try an idea for their PhD students. It's more of a merit allocation scheme. It's like how we run the supercomputing access. The researcher would propose a scientific problem that they want to solve and say that we need computing resources to solve it. So we can do something similar in this context. The education space, we're aiming for other quantum computing boot camps. And I mentioned this quantum computing merit allocation scheme, which going forward might be a real way of enabling quantum computing growth in Australia. and for the scientific community. So on the quantum computing framework, QuEra, right, the partnership, we really are thrilled to actually have a really deep partnership with QuEra. And this partnership isn't just with Pawsey, but also with joint projects with actually a couple of research institutes and universities in Australia and abroad. So we work closely with the University of Western Australia. We also work with Australia's Commonwealth Scientific and Industrial Research Organization. So this is the government agency essentially looking at scientific research. The Lynx Foundation in Italy, NERSC in USA, even ACE in Japan. All of these centers, and some of them are HPC centers, right? NERSC is an HPC center. So like us, their focus is on HPC, but they are looking to explore quantum computing technologies as an addition to the HPC ecosystem. Like you have GPUs, like you might have other accelerators, quantum computing, it would be viewed as an accelerator, enabling scientific discovery or just research in general. ACE is a similar sort of idea, but in Japan. And so these centers, they're very keen on looking at the integration of quantum computing with HPC, as well as algorithm development and running on real-world quantum computers. Just to kind of give a breadth of the projects we're looking at. So we are looking at optimization problems and looking at if they have efficient scaling on QuEra's machine Aquila. There's a continuous time quantum walks. There's a variety of different techniques we're looking at, but basically we're exploring optimization problems geared towards the near-term system, so Aquila, and with a line for future systems developed by QuEra, like the Gemini machine, that's gate-based. Machine learning, it's the same thing. We have a couple of interesting projects involving imaging processing and radar data, maybe prediction of negative health outcomes given a medical history and current health. So this is one of the possible applications to quantum reservoir computing. And there's the more academic outcomes of looking at quantum systems. In this case, it would be inflation and leptogenesis, because there are some research institutes that are very keen to try to explore quantum fields and the evolution of quantum fields. And this, the access of a real-world quantum computer might enable some interesting exploration. There's also looking at noise, exploring Markovian and non-Markovian noise, and how that might affect the systems and how they behave. It's very important to understand how systems behave and how real-world quantum computers might behave compared to the ideal. And in part, actually, I want to jump into the scientific collaboration between Edric, who's at Pawsey, and Jonathan, who's at QuEra, which is looking at how you might get a quantum continuous time quantum walk to essentially amplify a specific target on a graph. What I've got displayed here is the pulse control for Aquila. So you're looking at the pulse control and the display, the placement of the actual neutral atoms, and an evolution of the states of a graph, where the size of the graph depends, it tells you the probability of identifying that particular vertex, and there's a phase information color-coded in as well. The key thing here is that the challenge faced from translating an idea to a real world, like actually running in reality and getting some sensible results, really requires a partnership. So there's a real scientific collaboration between QuEra and Pawsey, exploring the actual application on Aquila and how we can translate the idea of continuous time quantum walks to an actual outcome that's producing what we'd expect given the system and its limitations. But they're really promising, and there's some really interesting possibilities for the exploration of this approach. And with that, I will end on the fact that the QuEra's Quantum Alliance has really been driving innovation forward. We've really benefited from the deep collaboration between the QuEra team, Pawsey team, and also the broader Australian ecosystem through research institutes and universities. Thank you very much.
Thank you, Pascal. Thank you very much for your presentation. I would like to give the word to Mike. Maybe in the meantime, while Mike shows his slides, I can ask very briefly, Ugo, how have you seen the Australian quantum community evolve and grow both in size and engagement since you started all the quantum computing activities at POSI Center that you briefly mentioned during the first part of the presentation?
Yeah, so what's being discussed in these days, right, is to build a national quantum computing test bed, right? We just started the conversation, but the idea is that going forward, the idea is really to work together with companies such as Q-CTRL and others here in Australia, Dirac and Quantum Brilliance, to build some kind of center similar to the one in Israel, right? Or the one in the UK, actually, where people can go deploy a quantum computer and then give access to the national community, right? The community here of researchers and scientists. That's what we started discussing. Other than that, there are actually many efforts happening in parallel. There are many grants that we're all applying for, but this is really the main coordinated effort that we started discussing here, right? So clearly the community is growing, a lot of interest. We see, for example, we are running in these days an internship program, right? We do have interns even at that level, like making tangible contributions to quantum computing. Last year, we had a person who out in 10 weeks was able to build a quantum tensor simulator that we're able to scale on 64 GPUs on our system, right? So what I've seen in the past 5 years, it's really a growing interest in quantum computing in general here in Australia, right? Exponentially growing, I would say, exponentially growing interest, right, in quantum computing in general. But, compared to other countries, we are still starting discussing projects that other countries have already implemented, right? So we're a little bit behind, but it's pretty exciting, right? There is a lot of interest, money coming from different parts of government, right? So it's happening. I mean, that's
Great. Thank you, Ugo. So, Mike, please, the floor is yours.
Great. Thank you so much. It's nice to be here. It's nice to get to chat with you, Tommaso and Pascal and Ugo. For those of you who don't know me, my name is Mike Biercuk. I'm the CEO and founder of Q-CTRL, and we're a company that's focused on making quantum technology, including quantum computers, useful really through software level innovation. We build infrastructure software that is tailored to solving the biggest problems in quantum computing and other quantum technologies. And the partnership that we have with QuEra is based around the software products that we build, as opposed to a more research style partnership, as you just heard about. Now, our business is focused on two key verticals. One vertical, and the one that we're going to tell you about today in this presentation, is quantum computing. Here we build infrastructure software that makes quantum computers perform better. It solves the fundamental problems of error and instability that we hear about so much. We heard about in the last couple of presentations, and our software is very widely deployed in machines all around the world. And we were the first independent software vendor to ever integrate with a third-party quantum cloud platform with another partner here, IBM, in 2023. In parallel, we have a very large effort on what we call software ruggedized quantum sensing, using software to solve the big challenges of hardware instability when we take quantum sensors from the laboratory to the field. And we've become a global leader in quantum assured navigation, having some of the first successful field trials of this technology in real moving platforms. But today I'll focus on the work that we do in quantum computing. It's the nature of the collaboration that we have with QuEra. We are a category-defining business in this field. We also successfully, like our friends at QuEra, I think within maybe a week or two of one another, had a congratulatory message on the NASDAQ wall in similar purple tones. So it's a wonderful color for our sector. But in this area, we are focused on solving the things that really matter. And that's what's gotten us to a point where we service government clients, we service commercial partners, all the major vendors, we service academic researchers, and we've been recognized for our contributions through a wide variety of awards for which we're very grateful, spanning EdTech awards for our products all the way through to the COVIs and Gartner cool vendor recognition. In quantum computing, you've heard at length the challenge that we face, that hardware is unstable, that it suffers from error. And this is the problem that we address. We build AI-powered error-reducing infrastructure software to solve these problems and make quantum computing useful. Our software is in the so-called middle of the stack. It connects the low-level physical devices to high-level abstractions and programming frameworks and applications. It handles everything in the middle that's required to go from the machine-level instructions that are sent to a quantum device up to the abstractions that make it easy for an end user like you to take advantage of these kinds of machines. And when I say AI powered, I don't mean some ChatGPT wrapper. I mean, for the last 7 years of our operation, we've been building our own machine learning tools that allow us to deploy machine intelligence to solve these problems in an efficient way. Now, we are a product-focused company, so we bring these tools to the market as different products tailored to the needs of different users. The tool that I'll tell you about in just a moment that really encapsulates this core value proposition is called Opal. It's for end users who want to run or execute quantum algorithms and get better performance, or vendors who want to integrate that capability natively, as IBM did and as our friends at Dirac, Oxford Quantum Circuits, and others are doing in parallel. But we also build tools for the R&D teams that are building quantum computers or studying what one can do with quantum systems, more like EDA tools, if you're familiar with the semiconductor industry. And at the end, I'll tell you a little bit about our Black Opal workforce development and skills training program. But really, starting at the core of it, running algorithms on quantum computers and getting better performance, the tool that's relevant is called Opal. This is a totally autonomous tool chain for suppressing errors that anybody can use. And anybody can use it because it's completely abstracted away. The end user doesn't have to tune anything. There are no options. There are no settings. In the background, there is a tool chain that suppresses errors everywhere they occur in the execution of a quantum algorithm. That spans from the actual definition of the machine language. What are the analog signals that we send to the quantum device in order to operate it, all the way up through to things like compilation and transpilation and crosstalk suppression and the like. All of these things have been built, validated, and created to be interoperable, such that with one line of code, an end user can execute this workflow and simply get better results. And what our users and partners see is really astounding. When this infrastructure software is coupled to a third-party quantum computer, end users can achieve things that were previously impossible. We've seen breakthrough results in a wide variety of areas, from network service fault diagnostics all the way through to pharmaceutical research from our partners at places like SoftBank and Mitsubishi Chemical and Mizuho, Deloitte, and many others, our friends at Blue Qubit here represented. Now, when these teams leverage our software on third-party hardware, what they see is measured in performance improvements of orders of magnitude, more than 10x improvement in the complexity of the algorithms they can run, measured by something called circuit depth, more than 1,000x validated improvement in performance, computational accuracy. How likely are you to get the correct answer? And more than 1,000x reduction in cost, improved efficiency, because these technologies are deterministic. There's no mitigation, as many of you may have heard. There's no need to run the algorithm over and over again with small changes. One and done, one shot, and you have higher probability of getting the correct answer, which is directly a cost savings or a time savings. But it's not only in near-term algorithms that we see these benefits. We also know that combining this kind of technology with quantum error correction, this logical level encoding for large-scale machines, can really boost the efficiency of the hardware you have. The big challenge we all know in quantum error correction is that it consumes a lot of devices. It consumes a huge number of qubits to encode quantum information in this protected way. Just running quantum error correction is a little bit like trying to cool a room when you have all the doors and windows open. As our friends in Western Australia know, on a hot day, it's not very efficient to cool a laboratory if all the doors and windows are open. The heat leaks overwhelm your system. The same is true in quantum error correction. But when you combine quantum error correction and the kinds of error suppression technology that I've told you about so far, the process can be much, much more efficient. So with the hardware you have, you can do more. It's like closing the doors and windows. It's that simple. And we've seen this in our partnerships, where with customers and with research partners, we can actually demonstrate that combining these two technologies together, error suppression and quantum error correction encoding, can be the difference between success and failure of quantum error correction. In this demonstration from our customers at Nord Quantique, they were able to show that when running a very particular form of error correction on their device, the overhead that's required really overwhelmed the benefits that they were getting, and they only got to break even. That is, all the benefits they got were offset by all the costs. But by combining these two technologies together, they could get beyond break even. So the quantum error correction was net advantageous for them as opposed to just being running in place. That's what happens when you combine these two technologies. But another very exciting part of our efforts is not only servicing end users and vendors, but teams that build devices, teams that study devices and study quantum dynamics on them. And here we focused on a tool that allows a lot of this machine learning technology and AI automation to be brought to the hands of researchers. With this, we've set totally new standards in hardware automation and the design of the machine language in these machines, in these processors, doing things like from cold start. That is a machine that has no device specifications, nothing calibrated, to hardware limited operation. For the experts, that would be T1 limited gates. 90 minutes, no human intervention. Completely autonomous with error handling and exception handling. This kind of capability comes from these tools. The exciting thing in our partnership with QuEra was about how we can combine our products and our offerings, not just our scientific expertise. And here we looked at combining Boulder Opal for control design and automation with Blockade from QuEra, which is focused on simulating the QuEra hardware. Now, this unison or this combination allows us to do some very exciting things and to push the limits of what's possible on the actual hardware from QuEra. One example, we looked at designing the machine language to operate the QuEra Aquila device that we just heard about from Tommaso. In this case, as a simple example, to generate a target state. That target state is alternating zeros and ones on the atomic states on this linear array. And that's represented by the red and the purple alternating there. Now, if you assume that your device is perfect, you can write down analytically what the actual control signal should be. A little bit like what I think Pascal showed in his presentation. And you can get part of the way there. You can partially generate the state. But by leveraging this quantum EDA type software, Boulder Opal, and accounting for the imperfections that one typically finds in the hardware, you can build what are called resilient or robust controls. And this is an example where you can immediately see in this color scale representation, by changing the waveform designed by Boulder Opal simulated on Blockade, we can generate a better representation of the state that we care about. Now, we can go further than that because it's not just designing the control that matters. It's also ensuring that it captures the peccadillos of the hardware. Nothing is perfect in this world. Everything suffers from small imperfections that overall can contribute to what dominates the achievable performance. And so we combine what's called model-based control design. You start with the so-called Hamiltonian, you design your solution, but then you can take that and combine it with closed-loop autonomous agents. You connect an AI agent in Boulder Opal directly to the QuEra hardware. That lets you get that last mile of performance. And we were very excited to show in an application note that anybody can view at our documentation site that by combining these two technologies, Boulder Opal with the QuEra Aquila processor, you could, in this case, demonstrate improved so-called Z2 state generation by about 3 times with 13 atoms in this particular experiment. As an example of what is possible when you combine control design with this very flexible analog hardware that QuEra has. And of course, you can start with this and build anything you like, generating any new target states. But I appreciate that there are some people on the call or who are watching this video for whom nothing I have said makes any sense. I appreciate that this has been an expert's game. And in order to overcome that, we also have focused very heavily in the last 5 years on skills training and workforce development. And for people that are new to this field or thinking about how they can leverage quantum in their workflows or looking to get into the field, we built Black Opal. Black Opal is the world's best edtech product for quantum computing, very widely used from universities all the way through to major corporates. It's an interactive product. It's like Duolingo for quantum. You can do it on your mobile phone. You can do it on your desktop. There are over 400 interactive lessons, fully visual, no math prerequisites. Everything is taught by inception in the process. You can earn a shareable recognition or certificate. And really, you can go from absolutely knowing nothing to programming a quantum computer without the formalism in math, but in a way that allows you to be quantum conversant. We've been very excited to roll this out at the state level in the state of Tamil Nadu in India, at the national level in the United Kingdom. It's the default skills training program through the National Quantum Computing Center, with whom QuEra is also a partner. And we've seen hundreds of thousands of activities completed and granted at this time almost 10,000 certificates of completion to end users around the world. So we'd love to hear more from you. We'd love to assist you as you're getting into your quantum journey or wherever you are on that journey. So please reach out and get in touch. Thanks very much.
Mike, thanks so much for this beautiful presentation. I have a quick question for you as well. So you mentioned several partnerships and customers during in your slides. How would you assess the sort of the market readiness to adopt quantum computing technologies and properly recognize their value, as the field continues to mature? One of the reasons I'm also asking this is also in view of or in light of the recent sort of roller coasters that, several quantum computing companies that are publicly traded, went through over the past few weeks.
So it's a great question. Thank you for the opportunity to chat about this. I think, the first thing to say is interest outstrips capability. Interest in adopting quantum computing is much larger, in my experience, than the ability of our sector to deliver. That's why we're all working so hard and we're all hiring so much. We know that recent pronouncements have moved public sector stocks. This is, in a sense, to be expected, and in my view, to be ignored by most of us who have a view towards making this real. We know, however, that the Boston Consulting Group says 90% of value capture will go to early adopters. And savvy enterprise and defense and government users understand that quantum advantage in quantum computing has not yet been delivered. And the exact timeline on which that advantage will be delivered for a killer app is somewhat indeterminate. We think from our engagement in the field that this is within the next 3 years, and it will be focused on optimization problems. It will be small incremental improvements, not exponential gains, but we think it will be high value. Others have different opinions of that. It will be revealed in the fullness of time, as they say. But savvy enterprise users get that, and they want access. And our job as a community is to make it easy for them to leverage these capabilities. So we as an organization have focused not only on how do we make it easy for an end user to get very high performance without writing tens of thousands of lines of code to implement their own error suppression or error correction, but also how all of that can be abstracted and how the end user can move away from programming at this assembly language-like level we employ, called the quantum circuit in digital quantum computing, and move up towards problem definitions. If you as an end user are focused on optimization and you buy a package like Cplex or Gurobi, you don't write in assembly for a CPU or a GPU. You write, solve optimization in a cutesy way. And that same problem level programming focus is what we and I would say our collaborators are working to bring, and we're very excited about adding this capability and abstraction through our partnership with QuEra.
Excellent, thank you, Mike. Hopefully, people will not be so confused, in the near future about the status of quantum computing, also the expectations that are put on so many quantum computing companies on the market. So with that, you can probably go through the last part of my presentation. Mike, if you can perhaps stop sharing yours, I can briefly upload my last part of the presentation. So I just want to sort of highlight a few ways of collaborating with QuEra. There is, of course, the possibility in terms of acquiring one of our quantum computers that, as you heard from me in the first part of this webinar, can be installed on site, provided with support, and also used as a tool to develop the quantum community. We already have a very close partnership with AWS Bracket to provide cloud access. It is a safe and remote access. It can also be accessed directly together with QuEra to start working on specific use cases, and also in the spirit of performing co-development projects like the one that, for example, we are pursuing together with the POSI Center and its end users to sort of co-develop what in the long term will become hopefully what are called the killer apps of quantum computing. In order to sort of boost the creation and expand the quantum ecosystem, we also recently launched the QuEra Quantum Alliance. We are very proud to have both Q-CTRL and Pawsey within the alliance. And the goal again is to help shaping the quantum community around the adoption of neutral atom quantum hardware and software and applications, together with partners that come from the research side or academic side, such as, for example, Pawsey and most of its end users, but also on the commercial side, for example, as Q-CTRL here on the call. And here we have partners that really come from all over the world, from the US, from South America, from Australia, as well as several from Europe as well. So with this, I would like to sort of conclude the webinar from today. I would like to thank Mike from Q-CTRL, Pascal and Ugo from the POSI Center. And of course, I want to conclude by essentially asking a question to our attendees. Are you interested in joining the QuEra Quantum Alliance? Are you interested in joining the partnership together, not only with QuEra, but also with the partners of QuEra within the alliance? If so, feel free to reach out to us. This is my email. If you have also questions related to this webinar that we were not able to respond properly during the presentations, feel free to reach out. This is my email. And if the question is not directly addressed to QuEra, I'm also happy to put you in touch with our partners from Q-CTRL and Pawsey. With this, thank you so much again, Mike and Pascal. And I hope to see you also at the next presentation from the QuEra World Tour. Thank you so much for your attention.
Okay, thank you. Thank you.
Thank you.
Thank you.